Hi, I'm Mike Glass with Orion Technical Solutions. Today I'm going to talk about the instrument transmitter test connections. There's lots of problems that occur due to misunderstanding of the typical smart 4 to 20 milliamp transmitters test connection and in doing the test measurements for calibrations and so forth. So I'm going to try to explain some of the issues with that. Um, Most of these industrial transmitters today, the 4 to 20 smart, so forth, they include a test connection along with the positive and negative terminals. So, what's this connection for, and how does it work? That's what we're going to go over today. The note on this, the connection diagrams and the detailed functionality vary from different equipment vendors, brands, so forth. Always consult your specific equipment references to apply this stuff. Don't assume that the bottom one is the test and so forth. Uh, how some of this stuff works will vary, but these concepts should help you understand what's going on inside much better, so you can make sense of the documentation and references better. Um, so the test connections provide a way to measure the loop current without disconnecting the transmitter signal leads. Uh, there's several advantages and reasons for that. One is it minimizes the wear and tear on the ferrules, the wiring, the terminal screws, and so forth. That reduces the chance of failure. It minimizes the chances of a short circuit. When you're disconnecting a wire and the circuit's live, there's a good chance you touch something you shouldn't touch. Next thing you know, you've popped a fuse in the ammeter, popped a fuse in the power supply, or caused damage inside the transmitter. It's pretty easy to do. And lastly, it avoids causing a power cycle in the transmitter. When you disconnect to insert your ammeter with a typical inline method, the transmitter shuts off for a moment. And that power cycle is a big deal, and we'll explain why that is later. So the test terminal in this example, I've got a typical transmitter laid out, very simple one, no intrinsic barriers and nothing fancy. I'm just showing the test. In this case, it's on the bottom. It's an extra terminal. Your main two wires, your field wiring, comes in the plus and minus, obviously. Let's see how this all works now. So there's a diode inside the transmitter. This represents what's happening inside the transmitter. The field wiring would come in over here on the left. So what happens is there's this variable resistor here represents the internal circuitry that's inside the transmitter that's regulating that 4 to 20 milliamp current. So in essence, it's adjusting its resistance to control the amount of current flow. There's a diode in between the negative in that path. So basically between the negative and the positive, there's a diode. But if you notice that little test connection is tapped in between that point where between the diode and the transmitter's regulating circuitry. We'll talk about how that works and so forth in the next slides. So this diode is basically the key to this whole thing. And let's explain how that works. So here's this slide. We take the transmitter, which is shown by the brighter, bolder yellow lines, and we're showing the field wiring on the right side of it. So typically what happens is your positive power supply comes into the positive, goes through that internal regulating circuitry of the transmitter, through the diode, and back to the PLC input card, through to its 250 ohm resistance to the negative. That's the typical setup of your typical instrument loop. Um, Notice how the current flows through the diode. It flows right through it. There's actually about a 0.6, 0.7 volt drop there inside that. You don't notice it. It's inside the transmitter. It's part of its overall voltage drop. But that's how the typical transmitter is working when it's in the field just running before you go out to test it. Now, if you go out to test it and you do I'll call it the old school, even though there's times we still use it, you hook your meter in series, and that's typically between the negative terminal and the field wiring. So we disconnect this wire from this terminal, we insert the ammeter in between there. We typically put it on the negative just to minimize the chances of causing a short circuit. It still can cause problems though. Um, so that shows kind of how we do it, next to the transmitter. But if we're analyzing this whole circuit now, look what's happened. The current's coming through, goes through the diode, it goes through the ammeter to get back to the wire, and then completes the circuit. So let's look at the next issue here. Is when I put this ammeter in, I'm going to momentarily disconnect that wire. Well, that's going to cause a power cycle, and that power cycle is an issue. So we'll talk about that coming up. Here's the way we do it with the test connection. We don't disconnect anything. What we do is we just hook the negative, in this case, for this particular transmitter that's shown, we hook the negative lead and the positive lead goes to the test connection. What that does, that puts the ammeter around the diode basically. And an ammeter, as you probably know, has low impedance. So what's going to happen is this current is going to come out, it's going to go through the ammeter instead of the diode, because why does it want to push through a 0.7 volt diode when it can go through a basically extremely low volt drop of the ammeter? So basically we just let the loop go right around, we let the current go through the ammeter instead of the diode. You don't even notice it as you're measuring. Interesting little thing, when I in the classes that I teach in the Orion Technical Solutions instrument courses, one of the things we do is we do a loop where we put a diode external to the loop and do the same thing, but it's not a diode, it's an LED, and it's awesome because the LED glows proportional to the current flow, just like it should, and we'll have a ammeter, 2 in series. We'll have another ammeter in the loop somewhere. And what's cool is when you put this ammeter across the LED, immediately the LED shuts off, but the current does not change. Nothing changes. It's the same exact current. So you can visually see that. I always like to make things as visual as possible. I might put a YouTube, drop one on our YouTube channel, a little video demo of that sometime soon if there's interest. So if that's something you're interested in, let me know. That'll kind of get me off my butt, and I'll do that. So uh, because this transmitter, because this ammeter shorts out the diode and basically the current remains the same, it's a really excellent way to measure stuff in our typical instrument loop. It's a way that we can do it without messing a bunch of stuff up. We don't have to worry about cycling power. That's super important because it could reset diagnostic alerts and other things in the transmitter. We need those diagnostic alerts. We need to know about them, and we need to be able to see them. And sometimes, a lot of times, techs are going out and they're just immediately disconnecting, putting their meter in series, and they never even see it. And then they hook up their heart communicator, and no, they don't see the alerts that were there minutes ago. And those alerts could have helped them know there's an issue coming up. Maybe there's a backup RTD, it's failing over and failing back, it's a loose connection, something like that. They could have found something if they wouldn't have reset those diagnostics. Too often techs are completely unaware of all of this kind of stuff, to be honest. Even techs that have gone to trade schools and so forth, a lot of the textbooks don't even cover this. If you work with safety instrumented systems, IEC 61511, ISA 84, SIS, uh, a lot of the times the procedures will specify that your testing has to be done this way because they don't want to wear out the terminals, they don't want to inject possible other faults. It's a much safer, easier way to do the testing, and it does not reset the diagnostics that are one of the things you're looking for in any, a real process safety type situation in SIS. So, couple notes. Since these diodes conduct a tiny amount of current, uh, there's there even when they're at 0. 0.1 volts, there's a tiny amount of current, and we're talking tiny. Uh, that could have a tiny impact. It's usually completely negligible. You can't even measure it, see it, anything. But if you had an extreme accuracy requirement, or if you have some kind of equipment that has what they call a high burden voltage on the ammeter, so maybe it's like 0.5 volts, 1 volt, higher than the typical Fluke 789, for instance. Those you could get in a situation where you get a little bit of accuracy mismatch, and we're talking real small, like 0.01 percentage band, stuff like that, 0.02 something. It's very small typically, but if you have those extreme accuracy situations, you probably want to dig in a little bit into this and look at there is information out there on the web and so forth, or you can reach out to me and I can kind of help too. Um, Most of our plants, we have tolerances of 0.5 to 1%, and we're operating in an envelope mode. So we don't really, a lot of times, we're not that concerned with exact accuracy. We're trying to make sure that we stay within that envelope. So it usually doesn't matter at all. And also, transmitters do vary how these connections are set up and so forth. So this is just to give you a basic idea how it works, when they're using that diode inside the circuit and so forth. So always consult your specific references, of course, when you're doing work in the field. Um, One note, if you're using these, be careful not to connect the test to the negative terminal and the other lead to the positive terminal. That happens sometimes. And when that happens, basically you short out the regulating part of the circuit. Well, that means you got 24 volts and basically no resistance. So it's going to pop a fuse. It's either going to pop a fuse in the ammeter or in the loop fuse, or it sometimes damages the diode. If that diode fails, and this happens pretty often, the only way to get the circuit to work again is by running the negative lead to the test terminal instead of the negative terminal, by the way the circuit's hooked up. Uh, to my knowledge, you cannot replace those diodes in the field. That's a transmitter. You're looking at a new transmitter if you want full functionality. It'll still work like that, but it's not right. You definitely then can't use this method of using the test connection. If you see that in plants where the negative wire seems to be going to the test terminals, it basically means whoever commissioned that probably didn't know what they were doing, or who did maintenance at some point didn't know what they were doing. They were touching stuff. They shorted something out, and then they just fiddled with it until they got it to work again. Maybe they didn't tell anybody, whatever. I see that fairly often when I travel around, look at customers' transmitters you open up, and I'm like, oh yeah, I know what happened here. It happens way too often, sadly, but that's kind of the nature of the beast. There's a lot of these techs are not trained. How are they gonna know? Um, the solution to these problems is training. You got to be trained, and not just trained on specific equipment. Even in vendor classes, I've sat in vendor class. I used to audit them and so forth, and the vendors don't seem to even really give this enough justice. Maybe they assume techs know all this. You got to be taught the fundamentals and how the 4 to 20 milliamp loop works, how the test connections work, and so forth. Um, Basically, we try to cover this and many other similar type issues that we've noted a lot of problems with in our INC type courses. You can visit our website at www.orion-technical.com for more info on that. And you can reach out to me in the links in the site there. Happy to help if I can. Good luck. Thank you.